Hello class. Today I want to cover chapter 13. This is the last chapter we'll cover in Chemistry 130. It's over equilibrium. Equilibrium gives us an indication of how complete a reaction is, how much product will be formed, how much reactant will be left behind. So most of the reactions that we've done so far in this class are reactions that go 100% to completion. So they only go in the forward direction. All the reactants are converted to product. But in reality, most reactions do not go to completion. And partly the reason why is there's more disorder in having some reactant left over in some product form versus all the reactant converting to all product. So we're going to focus on four things: the reaction rates, chemical equilibrium, equilibrium constants, and factors that affect equilibrium. So you probably have heard of the word rate before, and you probably think of rate as like travel. So that's what we probably that's most frequently the way we hear rate, like as you're driving down the highway, you're traveling in miles per hour, and so miles is a distance and hour is time, and so the higher the speed, the higher the rate of travel. So in chemistry, what we focus on is the change in concentration of reactants and products over the change in time. So our rate's going to be change in concentration over change in time. And so I kind of like this picture because what you see is, you think of a car traveling, and it's traveling in miles per hour, and then the car collides with something and it deploys the airbag, and there's a chemical reaction there, and the chemical reaction happens at a rate faster than the car is traveling, and that allows the airbag to expand, and so it cushions the dummy from hitting the steering wheel there. So rates of reactions for chemical reactions, they can be different speeds or different rates. In this case, this one's faster than the actual collision. So one of the misconceptions I find with people is that when a reaction happens, it has to overcome an activation energy. So when you pour two liquids together and there's a chemical reaction, it doesn't happen in one step. It generally requires multiple steps. Bonds have to be broken, other new bonds have to be formed before you can get to the product. So for example, let's just look at something as simple as the formation of water. So with water, water is formed by using hydrogen and oxygen. And let me see if I can draw it here. So we have hydrogen gas and we have oxygen gas, and then we form water, liquid. And this equation's not balanced, and I'm not going to balance it, but I just want to show that this bond has to be broken, and this bond has to be broken, and two new bonds have to be formed between the hydrogen and the oxygen. So for this to happen, there is an activation energy that has to be overcome before the product is formed. Before the water is formed here, there's an activation energy required to convert these two molecules into a kind of what we call an activated complex. It's neither the reactants or the products before we get to just the product. So activation energy is measured from the energy of the reactants to the top of the peak here, to the top of the energy required to for the reaction to continue. All right. So in this case, this is an exothermic reaction. So let me say what that means. The reactants are at this energy level. The product is at this energy level. So when we get finished with this reaction, this amount of heat is going to be released by the reaction. And that's what we actually see here. When hydrogen and oxygen react to form water, this releases heat to the environment. And you may have seen like rocket engines that are based on this reaction. So this releases heat to the environment. And so that's called an exothermic reaction. I'll just say exo for short. In this other plot, we see that here is our reactants. Here's our products, which are higher in energy. And so again, we measure activation energy from where the energy of the reactants are to the top of the peak. But in this case, when we finish this reaction, the products are higher in energy than the reactants' initial energy. And so for this case, this reaction has to absorb heat in order for it to happen. And we call that an endothermic reaction. So if you were holding a container where an endothermic reaction was happening, the container would get colder. It would feel colder because it's pulling the heat from the surroundings into the reaction. So what determines this, or the theory that we use to describe this, is called collision theory. All right. So what we're saying here is that molecules collide. So we have a hydrogen and oxygen. They collide with one another. The bonds break, and then new bonds are formed to form these water molecules. All right. So we get, actually, if we were going to balance this now, we put a 2 here, right, and a 2 here. And so we need two hydrogens. So there's my 2 hydrogens, 1 oxygen, and then 2 hydrogens attached to each oxygen. So it's not just a matter of collisions, it's effective collisions. A collision has to have enough energy to overcome the activation energy. And it has to have the proper orientation. So maybe if the molecules collide end on end like this, like that was a water molecule, a hydrogen molecule, and that was a oxygen. So if this was a hydrogen and this was an oxygen, if they collide end on end, it may not cause this reaction to occur. So that wouldn't be an effective collision. So collision theory says we have to have effective collisions with enough energy to break bonds and allow new bonds to be formed. So what I want you to get out of these slides is these things that are in bold, definitely know these definitions and also the application of those definitions. So if I gave you either one of these plots and I asked you to label where are the reactants, where are the products, describe what this line from here to here is, or could you draw the activation energy, and then describe what this means here. Same thing here. Can you describe the activation energy? Can you tell me this is an endothermic reaction because the products are higher in energy than the reactants, and that this is exothermic because the products are lower in energy than the reactants. So that's what we're looking at. So let's look and see what this looks like as far as now we look at it graphically here. So before the collision, we have maybe a chlorine here and nitrosyl chloride here, nitrogen, oxygen, and chlorine. And so what happens is these collide. The 2 chlorines stick together. All right, this is the activated complex in here. Somewhere up in this region is the activate where the collision. It's not yet it's not the reactants, it's not the products. And then after the collision, we end up with this. All right, so what I would expect you to be able to say is this is the reactants before the collision. This is called the activated complex, and then this is the product. Now, in this reaction, and then we would call this an effective collision. Effective. Why is it effective? Because the product is formed. We see that the products are formed here. In this collision, they collide, but they don't collide with as much force as this one, as evidenced by this illustration. So what happens is the chlorine just bounces off. It's an elastic collision. The chlorine goes this way, and the other reactant, the nitrosyl chloride, the NOCl, if you want to write it that way, goes the other way. So this would be an ineffective collision. So not all collisions are effective. And in order for a reaction to occur, it has to be an effective collision. So again, you have the reactants, you have the products, you have the activated complex, something in between. And the other thing that you need to realize is that from here to where the products lie, that tells us that because the products are lower in energy than the reactants, this is an exothermic reaction. It releases heat when the reaction occurs, when we have effective collisions. So be able to label it. Also, make sure that you know the what the axes are. Y-axis is energy, and the x-axis is reaction pathway. Also, I see it stated as reaction progress. Oops, wrong way. All right, so here is the postulates of the reaction rates and effects of collision theory. According to collision theory, the rate of reaction depends on the number of reactant collisions. That makes sense. You're not going to get any new products if they don't collide together. So it is the number of collisions and the energy of those collisions. So those are really important. If you don't have enough energy, just like we saw in the previous slide, in the second example, we didn't have enough energy in this collision, and therefore the reaction didn't happen. So as the number of reactant collisions increases, we should get an increasing, how do we get the increasing number of reactant collisions? We increase the number, the concentration of the reactants. So the higher the concentration of the reactants, the more collisions possible. Now, we have to have enough energy that when they do collide, that a chemical reaction occurs. And so that's what we mean by effective collisions. So you have to have enough energy and enough for the reaction to actually form the product. And that's effective collisions. So another way to increase the frequency is to increase the temperature. That's important. So, as the temperature goes up, the kinetic energy, the energy in motion goes up. And so the higher the temperatures, the faster the molecules move, the more energy they are going to have when they collide with other molecules, and the more likely we're going to have effective collisions. So chemical equilibrium is a reversible process. Make sure you understand this, that chemical equilibrium occurs when you have a reversible process. So we've talked about strong acids, and we said hydrochloric acid, when placed in water, and I'll put H2O here, forms hydrogen ions and chloride ions. And this is aqueous, and this is aqueous. That reaction goes 100% to completion. 100% to completion. It's not reversible. And so that's not the type of reaction we're talking about in this chapter. What we're talking about is if we take a weak acid like hydrofluoric acid, and we've defined what weak acids are in a previous chapter. So hydrofluoric acid, when you add it to water, it too forms the hydrogen ion and the fluoride ion, but it's reversible. These two ions will combine and form the molecular hydrogen fluoride. And so because we see the double-headed arrows here, the reaction is reversible, and when we have reversible reactions, then we can have a equilibrium process. So initially, when you add this to water, there will be a surge for this reaction to go towards the products. Once the products are formed, and there's a fair concentration of this, some of the products will revert back to the reactant. Eventually, this is the important part right here, that the forward and reverse processes are occurring at the same rate. So eventually, the rate of the forward and reverse processes occur at the same rate, and when that happens, you are at equilibrium. All right? Now, I can show you kind of what this looks like physically. It's kind of like, you want to think of it as a seesaw. You first get on the seesaw, first person gets on, and you have your reactant over here, right? And then another person gets on the other side, and maybe if this person weighs a little more, it goes the other way. But eventually, maybe you throw a ball back and forth or something like that, and you eventually get to equilibrium, where both forward and reverse, as far as the gravity goes up and down like this, they're equal this way and this way, right? And so we get an equilibrium that way. So that's what we're looking at here. We're trying to get to where the forward and reverse processes, the rates become the same, and therefore we reach equilibrium. So this is what it looks like chemically. This is a nice picture to show you what's going on. So we start off, what we're doing here is we're starting off with a colorless substance in dinitrogen tetroxide, colorless, all right? And this substance is going to separate into two nitrogen dioxides. And this reaction is reversible. So initially, you start off with nothing but reactant, N2O4. And it's colorless. And so what you see is you start off with a high concentration of dinitrogen tetroxide. You start off with 0 of the nitrogen dioxide, and that makes sense because when you initially start the reaction, all you have is the reactant. So over time, so look at the axis again, it's time on this axis and concentration on this axis. And remember what we said rate was? It's the change in concentration over the change in time. So what we see is the concentration of the dinitrogen tetroxide decreases over time, and eventually it levels out. The change in concentration over change in time, the rate becomes constant. And then what we see with the nitrogen dioxide is initially we had 0, but now some is formed, and so the concentration of the nitrogen dioxide increases. But eventually it levels out too. The rate of the change in concentration over the change in time of the nitrogen dioxide is the same. So that's what these two slides or these two slices are showing. Notice if we count the number of dinitrogen tetroxides and the number of nitrogen dioxides, they're the same for both of these. So at this point, the rate of the forward and the rate of the reverse are the same, and that's what we're looking at in this region out in here where it's flat. All right, so that's what equilibrium is. This is what it would look like if you can see it on the molecular scale. And what you see in the lab is this. You started with a colorless solution and you end up with a colored solution. And so when this color is not changing, we assume that we are at equilibrium. So you go, why do I need to know this? Well, in biology, we would call this homeostasis, right? We would say that at equilibrium, we have a balance here. Everything's balanced. And then we're going to learn like what happens when I apply stress to this system. So that's where we're going with this. So there is a mathematical way to describe what we just saw. So we have the reaction. The colorless dinitrogen tetraoxide forms 2 moles of nitrogen dioxide. Well, mathematically, the way we express what is happening is we put the concentration of the product in the numerator. So this bracket represents that this is concentration in moles per liter. So we've talked about molarity before. So you need to know what the molarity of the nitrogen dioxide is, the product. And in the denominator, you put the concentration of the reactant. You put the concentration of the reactant here. Now, there are coefficients or powers that go here and here. So where do we get those? Well, we get them from the Bound's chemical equation. So the coefficient here in front of the dinitrogen tetroxide is 1. So we don't put any 1 here. It's understood there's a 1 there. But here the coefficient is 2. So we place the power of 2. We raise the concentration of the nitrogen dioxide by 2. So this is, and this ratio of product to reactant equals the equilibrium constant. Now, what is a constant? It's something that doesn't change. And so as long as the temperature remains constant, the equilibrium constant will also remain constant. All right? So as long as the temperature doesn't change, K is a defined value. And this ratio, there's an infinite number of combinations that you could make this, and the ratio would always come out to be the same. So for example, you could have, after you square it and everything, you could have 16 divided by 4, and that would give you a constant of 4. You could have 8 divided by 2. That would give you a constant of 4. I mean, you could go on and on here. 80 divided by 20. There's an infinite number of concentrations here that when you divide the numerator by the denominator, you would get the constant 4. So that's what we're talking about. And the only thing that can change this 4, it's not the concentrations. The only thing it will change, the 4 is constant. That's fixed. The only thing that can change this is temperature. So these have to equilibrate or to settle out or to become constant, have certain constant rates that equals 4. The ratio always has to equal 4 at a particular temperature for in this example. So what I want you to do is I want you to write the equilibrium expressions. That's when we write it all. K equals products divided by reactants. When we write that entire, let's just go back to make sure. When we write this entire, and let's erase that just to make it a little better. Okay, so we can do that. Oops, it's not going to let me do that. All right. Well, let me try. Yeah, I can. Let me try this. If I click that and all right, and let's try that. So this entire mathematical expression is called the equilibrium expression. So you got to get the wording right. This is the equilibrium expression. This is the equilibrium constant. And the expression is always the products divided by the reactants raised to their appropriate coefficients. Okay? So now what I want you to do is I want you to go to this slide. And I want you to write the equilibrium expressions for every one of these reactions. All right? Write the equilibrium expression for every one of these reactions. Now, we know these reactions are all reversible because they have the double-headed arrows here. Now, this is an unconventional way to write it. Generally, we see it as one arrow up top going forward and one arrow going in reverse. So let me just kind of show you that. So normally this is the convention that we use. That's what we normally would see. But for this problem, they wrote it a little differently. Okay, so what I would recommend is you stop the video or pause it at this point, write the expressions, and then see if you get the correct answers. All right, so for the first one, we start with the equilibrium constant K. My products are ammonia. It's a gas. If you want to put that in there, you can. Close the parenthesis and put a power of 2 there because that's the coefficient. So there we have that, and we divide that by the nitrogen and the hydrogen. And again, we raise that to the third power because the coefficient here is 3. All right, the next one we would have equilibrium constant equals the product raised to the second power divided by the hydrogen concentration and the iodine concentration. I guess technically we don't have to put gas here because we're talking about concentration. So that may lead us to something else if we say gas there. All right, the next one, you have this complex called the silver ammonium complex, ammonia complex. So we have that concentration. We divide that by the concentration of the silver ion and the concentration of the ammonia raised to the second power because the coefficient here is 2. For this one, we'd have K, the equilibrium constant, is equal to the oxygen concentration raised to the third power divided by the ozone concentration raised to the second. So the third, the second goes down here. All right. The next one we have cadmium bromide. And so we have cadmium and in the denominator we would have the cadmium ion concentration and the bromide ion concentration. And this would be raised to the fourth power because the coefficient here is 4. And then the last one, we would have concentration of the dinitrogen, nitrogen dioxide raised to the second power divided by the nitrogen oxide raised to the second power times the oxygen concentration. So that's how you do it. It's fairly easy. You just products over reactants. Each substance is raised to the coefficient within the balanced chemical equation. The equation must be balanced for you to do this. Here's what they look like. So you can check your work again there. Much better drawing than mine. All right, so this next problem is they want you to determine the value of the equilibrium constant. All right, so notice the first thing is it's at the same temperature. So temperature determines what the value of the equilibrium constant will be. So to do this problem, you have to write the equilibrium expression first. K equals, and you would say, well, it's the concentration of the carbonyl chloride, and also called phosgene. That's the common name. But carbonyl chloride, generally what I call it. All right, and that is over the reactants, carbon monoxide and chlorine. All right, so before we start the problem, let's make sure it's balanced. We got one carbon, one oxygen, 2 chlorine, 2 chlorine. So this one's balanced. This is the equilibrium expression for this chemical reaction. And then they give you the equilibrium concentrations of all the species. So what that means is you're going to put a K here equals the concentration of the carbonyl chloride, which is given right here, 0.14 molar. And then you're going to divide that by the concentration of the carbon monoxide, 1.2 times 10 to the negative 2 molar. And then you're going to divide that by 0.054 molar for the chlorine concentration. Now on your calculator, you're going to take 0.14, you're going to divide it by 1.2 exponential negative 2, then divide by 0.054. If you do that, you'll get the correct answer. Or some students like to do this. They like to say 0.14 divided by parenthesis, this times that, close parenthesis. I don't care which way you do it. You should come up with the same answer. And let's move to the next slide so you can see that. All right. So you should get for an answer. Yeah, this does not look correct. All right. So I'm going to have to calculate it out on my calculator real quick. So let's talk about it again. What I would do, I would say 0.14 divided by 1.2 exponential negative 2, and then I would divide by 0.054. So I do get this as an answer. All right, that's right. That answer is correct. All right, that answer is correct. Let me erase that. I just looked like a huge number for me, but it is correct. All right, so the answer is 2.16 or 216. But we only have two significant figures in these numbers, so we have to report this to two significant figures. We go 1, 2. The 6 causes this to round up to a 2, so we would get 220. And 220 in scientific notation is 2.2 times 10 to the second power. All right? So I find students get confused here. They got this for an answer as multiple choice, but you got this number. Yes, these are the correct values. This is the not correct because of the number of significant figures, but when corrected for significant figures, it does make 220. All right, so just be careful about that. Make sure that you don't say, "Oh, I don't have the right answer." You might have it. I mean, I would definitely start thinking you have the right answer if you're only off by 4 there. So just keep that in mind. All right, so the magnitude, which is how large or how great it is, the magnitude of K tells you how far to the right, how far does the reaction go to completion. All right. So if K is very large, let's just do a general equation here. If you have A going to B, and if I write the equilibrium expression for that, that would be K equals the concentration of B over the concentration of A. If K is very large, that means this term is large and this term is smaller. So that B is much larger than A. Now you can make this ratio large by either B is really large or A is really small. Either one of those, B being really large, A being really small, is going to give you a ratio that K is much greater than 1. It's going to be large. So when K is large, when it's a large value, like they're saying 1 times 10 to the second or greater, which is 100 or greater, that tells you the product is favored over the reactant. Because as the product increases in concentration and the reactant decreases in concentration, the overall K value will go up, the equilibrium expression. So to get large values for K, B has to be large, A has to be small. But remember, what determines K is the temperature. K, the equilibrium constant, is determined, the magnitude of it is determined by the temperature, if all other things being equal. All right. So then the opposite happens. If you want a K that is very small, that means A is the larger value, B is the smaller value. So when A is much, much greater than B, you're going to get a K that is very small. So if the K is less than 1 times 10 to the negative 2, which is 0.01, then we consider the reactants favored over the product. That means A mostly stays as A and does not convert to product B. So K does indicate to what extent the reaction goes. So K much greater than 1, K much, much greater than 1, the products are favored. If K is much, much less than 1, then the reactants are favored. And then K around 1, They're going to have a nice mix of both. Neither products or reactants are going to be favored. They're going to be about equal, right? If K equals 1, that means the concentration of B and A are the same, right? So you're going to have a mixture of both at equilibrium. All right, this is where we're going to stop this video. I'll make another video to finish out chapter 13. But I think this is a great place to stop because there's so many parts to Le Chatelier's principle here.